You are audible. We are able to listen. Please share your screen.
Good afternoon, ladies and gentlemen. I will tell you about the boundary element method for three-dimensional problems of electromagnetism.
So you have any presentations to present? Any PPT? Will you be presenting with the PPT?
Yeah.
Okay. So can you share your screen?
Just a moment.
Sure, sir. And also in the meantime, please introduce yourself, sir. About you and where are you from now? Your field of interest of research.
I'm Valentin Ivanov from Russia, and Can you see my screen?
No, sir. So you need to press a share screen over there.
Share screen?
Yeah, you need to click on the share screen. There, first you need to open your. There you go and click on your presentation PPT.
Oh.
Yeah, now it has been shared, sir. Yeah, you can press from beginning.
Now you can see.
Sir. Yes, it is visible. It is visible. Please go ahead, sir. Introduce yourself, and then please go ahead.
I'll give just a brief introduction in the boundary element method about some mathematical aspects, and also I will present some examples of industrial application. The problem of electron optics includes as field equations, equations for particle motions, continuity equations, and material equations. Different applications area demand different numerical methods to simulate those complex three-dimensional problems. One devices are very powerful RF generators. Another one, the application for night vision devices, mass spectrometers, and also there are different formulations for the field problems. The most popular are partial differential equations, which apply mostly finite difference method, variational problems, which apply minimization of some functionals, and integral representation, which use integral over the boundary and over the space. All these methods are in some sense equivalent. So there is a procedure how to transform one method to another one. For the integral representation, the boundary problems create so-called Decomposition boundary condition, Neumann boundary condition, which can be represented with different integral equations. Here, first integral is double layer potential with density mu, and second integral is the single-layer potential with source density sigma. For Newman condition, we have zero integral equations, but all these equations has the kernel, which in simplest case is the kernel is 1 over R, where R is the distance between observation point and source point. And you see that when observation point very close to the source point, we have singularity. And there is very simple procedure how to regularize this equation. So instead, the clear boundary condition, we have reduced equation where first integral is regular and second one can be evaluated analytically for an arbitrary surface shape. The boundary element method can be approximated as on structured mesh, as on unstructured one. For structured mesh, we use so-called parametric surface representation. These equations represent three-dimensional surface. And when we use polynomial approximation for field source, for example, for charge density, we can obtain a matrix element for large linear system when we use numerical quantities to evaluate integrals over the surface element. Unstructured mesh can be represented by a set of triangles over the surface. And the feature of this representation is that all integrals, for example, field integrals, can be evaluated analytically, which resolve the problem of singularity. Analytical representation is not very simple, but in any case, it can be evaluated much faster than numerical evaluation for all integrals over the surface. Then we use singularity analysis to evaluate the derivatives for the potential field strength. Using some simple mathematics, we can evaluate all limits for these singular members of our equation. And in order to evaluate integrals over a space for space charge density ρ, we can use also linear approximation for the field source, and then we can evaluate all integrals for potential as for field strength analytically. You can see the final integrals for the potential and for the field gradient. And the convergence for linear and piecewise constant approximation for field sources, you can see that the rate of convergence is very fast. First example for industrial application is the Electron gun for 74 megawatts sheet beam klystron, which have been fabricated at Stanford Linear Accelerator Center. You can see two versions. Diode gun consists of two elements, cathode and anode, and triode gun includes three elements: cathode, grid, and anode. We provided simulations for these electron guns for both structured mesh, this picture, and for unstructured mesh with triangle elements. And you can see that the problem of beam focusing can be simulated using normal desktop computer for probably 20 minutes of CPU time. And next slide shows the gun assembly, which can be fabricated at SLAC. And this prototype has been tested and shows the very good efficiency in collaboration with the company Electron at California. The difference between finite elements and boundary elements is the boundary elements create large matrix with just small band, but boundary element create the matrix of linear system, which is dense. So in order to simulate very complex problems, which include many electrodes, we can provide decomposition of our complex system onto simple blocks. And then we can provide iterative procedure over each blocks and obtain the final solution for very complex system. And the formula below shows the efficiency of computation depending on the number of blocks, K blocks, and L is number of iterations. You can see that we simulated very complex electron optical system with more than 100 electrodes, and this graph shows the conversions for different approximation with using piecewise approximation and trilinear approximation. And the graph below shows we can evaluate the fourth order derivative from the field. And this graph is very smooth, which demonstrates that we have very high accuracy in our calculations. With using this approach, we can simulate physical instruments where we have many different kind of beams. This beam is electron beam. But then when electron beam hit the anode, it produces the ion beams. And we can simulate both beams with the emitter, which is unknown originally. And this form of emitter can be evaluated in our simulations. And this thermonuclear device, plasma trap DOL3, has been fabricated in Budapest Institute of Nuclear Physics at Novisibirsk. Here you can see a very complex section of next linear collider, which consists of 65 cavities of complex shape. And this coupler is input energy coupler and output coupler. And you can see below, in the middle, you can see the decomposition of our complex system onto blocks, and each block can be simulated on the parallel computations. The color shows different colors shows different processors. And below you can see the electron beams, which shows a red color, which shows a green color. And these electrons hit the wall of our cavity system and create secondary electrons. So primary electrons show red color, and secondary is shown with green color. This problem includes few million particles, and in parallel computations, the large system includes 15 million elements. Next slide shows the integral representation for harmonic oscillation in the RF cavities. Here, the kernel of integral equation is a tensor of second order tensor, and we can evaluate matrix elements. Also, as in previous our examples, and by some way we evaluate singularity for these integrals, and you can see the chain of cavities, and below each cavity has different shape of these windows in between the cavities. So this structure is pretty complex structure in 3D. And relative error for the main frequency was about 0.005%, when the number of elements was 826. So these examples shows that we can very high efficiency for our numerical algorithms to simulate complex problems of electrodynamics. So summary, we evaluate analytical technique for precision evaluations of the field distribution and its higher order derivatives. Then we implemented a set of computer codes to simulate the different problems of electromagnetic field, as for harmonic oscillation, as for non-stationary problems of electrodynamics. Thank you very much for your attention.
Thank you, sir. Thank you. It was a wonderful presentation and very nice to see the mathematical functions which you have done with respect to electromagnetism, and it is very much required in the analysis field, basically in meshing and all. So thank you, sir. I would like to connect and learn more about it. Thank you, sir. Anybody would like to
Thank you
ask?
very much.
Yeah. Anybody would like to ask anything to Mr. Valentin?
I would show some examples of my books.
Oh, that's
I
really nice to
published.
know. Okay, wonderful.
So thank you very much for your attention.
Thank you, sir. I'll connect with your person. I'll text you. So thanks a lot, sir. It is wonderful presentation with respect to electromagnetism and your meshing and all. So thank you.